just to make things different, I'll do this on Windows 2008 in this class instead of 2003. He's like, damn it!
Damn it. That's cool.
So I'm gonna do it in VM player here.
You've done 2 class?
Yeah, that's
It doesn't matter. 6 in one hand, half dozen in the other.
yeah.
All right. You suck. Yeah, go ahead. Alright, well, we'll see if that works later on. Alright, so I updated LAB2. It's a different thing, it's a different document. We are going to continue on with chapter 5 tonight.
Chapter 6.
My fault, chapter 6 tonight. Yes, chapter 6. Yes, firewalls and security appliances. So, we've talked about routers and how they're used as firewalls. Now we're going to actually talk about firewalls themselves. The big difference is in the applications and usability and ease of configuration with dedicated firewalls versus and security appliances versus routers. Okay, because all a firewall or firewall appliance is a router that has a bunch of additional applications or features that you configure. The main takeaway that I want you to look at here tonight, we're going to talk about a couple different types of firewalls. We're going to talk about what every firewall must do. Every last one, there's 3 things that they have to do. Okay? Okay, well, let me step back. There's 2 things that they have to do. They have to NAT, they have to filter. Because if they don't filter, they're not a firewall. And if they don't translate public space to private space, it's not really a definition of a firewall either. Used to be that there used to be 3 things. They used to have to route as well, but now there are transparent or stealthy firewalls that don't even have to do that. They basically act as a bridge, which is one of the first things we're going to talk about here after we talk about hardware and software firewalls. Hardware firewalls typically work at layers 1 through 4 of the OSI model. Software firewalls can work all 9 different layers. And with software firewalls, they have more of a system impact, where network firewalls have more of a performance impact on a network. Hardware defends the edge, software defends applications and data. Different firewalls we'll talk about. We're only going to use the 5510, the ASA, a little bit later on. But you can also make them with Linux IP tables. Cisco Security Agent is a host-based firewall. There's dozens others, McAfee, Symantec, Trend Micro, yada yada. And then there's open source based applications that can act as firewalls as well. So, with the ASA, they come in 2 modes. Traditional routed and transparent or stealth. Okay? In the let's talk about stealth firewalls first. Typically, a stealth firewall is going to what we call be a bump on the wire. It is going to sit somewhere on the segment between your outside internet and your inside network. It may have only one IP address, which is a management address. That management address may be on the inside network, but for better security, you can have it on a out-of-band network. You have, say, one workstation that only attaches to that out-of-band network. Therefore, it cannot be compromised, and the administration of the firewall has to happen for that one workstation. Again, very secure, but not practical. So it may have one IP address from that network. It's going to translate or NAP, all right, statically, and it's going to have ACLs. All right. It is not typically going to use port address translation, because port address translation has to be a physical IP if it's overloading on the network. All right. The reason for that is, for this to be a true stealth firewall, you want it to have zero visibility from any network. Therefore, if I can't see it, I can't what? I can't attack it. If I can't see it, I can't attack it. Which is a good thing, right? Now, there's a couple things that you don't want to you can't necessarily do with a stealth firewall. Okay? You can't do. One of them is VPN. If I have a VPN here, I can't, if I need to use this as a VPN, it's got to be a routed firewall. Because I have to terminate the VPN connection on an IP address. Have to. Alright, so that's transparent or stealth. Traditional routed can be set up the same way. The big difference is I now have separate networks, even multiple networks, and I have IP addresses that are attached to the different networks that are on the firewall, and then I must route between the different networks or the different interfaces. So that's the difference between a transparent and a traditional routed firewall. Do I have IPs? Do I not have IPs? Stateful inspection. Okay, we talked about this a little bit last time around. Okay, we talked about established connections. What's an established connection? What's an established connection? What do I mean when a connection is established?
When it started from inside the network?
Not necessarily. Yes, it can be started from inside the network, or it can be coming from outside of the network as long as I have a hole through the firewall. Once, basically, in short, it's a fully nailed up TCP three-way handshake. Okay? Once I have a TCP three-way handshake between two stations, that's an established connection. Okay? New connections are just that. They have not gone through that full establishment yet. Okay? In stateful inspection, what ASAs can now do is they have enhanced feature sets, and they can look at some layer 7 applications. Alright? And they can inspect, or what we call do deep packet inspection. Alright? The order of operations for the ASAs on page 150 and 151, very similar to what we talked about in routers. Security context. Now this is the creation of multiple virtual firewalls within one single firewall. It's basically the creation of a VM or partitions within the ASA. But if you do this, it's like a transparent firewall. Some features, such as dynamic routing or VPNs, are not supported. So you have to keep that in mind. In essence, it's like making a firewall on a stick. Okay? Similar to a router on a stick. The security context can be set up in both routed and transparent mode. Okay? Security levels. I have an example of that up here on the board. Alright? Security levels define and identify which interfaces are trusted and which must have some sort of inspection to pass. The higher the number, the more it's trusted. So, we have to do two things with the different interfaces when we set them up on a firewall. Now, in a traditional router, we just have to give it an IP address and turn it on. We're done. Right? Still got to do that if it's in routed mode. Still have to do that. But we also have to do two additional steps. We have to name the interface, and this is used for defining network address translation and to define your access groups. And we have to give it a security level. Now, security levels are a trust basis, and when I name an interface, there are two different named interfaces that will automatically populate the security level variable. That's outside and inside. The outside interface is always going to default to security level 0. The inside interface, when you use the name if inside command, is always going to default to security level 100. The least trusted level, the most trusted level. If I create additional interfaces, I can name them whatever I want to. DMZ, Bobo, Bozo, Mustang, Camaro, doesn't matter. But when I do that, I have to manually give them a security level. Okay? Now, in a lot of networks, you're going to have a DMZ. Your first DMZ, you want to, by best practice, you don't have to do this, you want to put it smack dab in the middle of these two, 50. You do that for one reason. That's if you ever have to create a second DMZ. If you have to create a second DMZ, you don't know whether the devices on this DMZ are going to be more trusted or least trusted to your primary DMZ. Therefore, you can go in either direction. This could have been more trusted. So I could have made this 75 instead of 25. Now what this does is the higher the number, the greater the trust. Meaning, I can pass traffic from a higher number interface to a lower number interface without having to put in an access control list. There's no inspection. So if I am passing traffic, say I'm trying to connect to a server, my mail server on the DMZ, I can do that without having to cross an access list. Conversely, if I have a server on the DMZ and it needs to access something on the inside network, let's say I have an e-commerce server here, and I have a database server as a back end with customer information, I've got to create a DMZ, or excuse me, an access control list for that traffic to pass. Because I'm going from a lesser secure interface to a more secure interface. Same thing with traffic from the internet. By default, the firewall is going to block all traffic, by default. Unless I tell it I'm going to specifically let something in. So if I have web servers, mail servers, DNS servers, e-commerce servers, World of Warcraft servers, I don't care what, on my DMZ, and I want to have traffic go to it from the internet, I've got to have an access control list with those policies defined. Yes?
Is 25 as low as you could go? Like, what if you were going to split it, like, one, like, you could add another network to that?
I could go
Like, would
24, 23, 22.
So you're saying if you go from a higher level to a lower level and you don't define an access control that you're covered, but if you have an access control, that gets a greater priority?
No, you shouldn't even put one in there.
You shouldn't even use one.
Nope, should not even use one. Should not even use one. Okay? You still have to find network address translation between the two interfaces as well in a firewall. Routing. Routing works in different ways in an ASA versus a router. Okay? It's still the same concept and principle. Commands are slightly different. but ASAs will support dynamic routing protocols such as OSPF, including OSPF version 3, RIP, EIGRP, EIGRP version 2. Okay? Of course it'll work with static routes. Static routes look more like routes that are set up in a Linux server than a traditional router. You don't have the IP route command, you have the route command. OSPF setup, RIP setup, and EIGRP setup are very similar, but instead of going into a router mode like you would in a router, you just give it OSPF network block instead of having to define your area and everything else. It's all done on one line instead of multiple lines. We're not going to do any dynamic routing with the ASA in this class. Everything we do is going to be with static routes. Okay? NAT, network address translation. It comes in two forms. Just like with a router, static NAT and dynamic NAT can work with both pools or with single individual translation lines. Port address translation, same. You can have static port address translation that overloads one single IP or an IP attached to an interface, or dynamic pools. Okay? NAT control is a way to bypass NAT altogether so that you don't have to set up NAT between two interfaces, even if it's a one-for-one NAT, or what we call a matching NAT. See anything else on NAT? You will get NAT down really good here in the in both routers and in firewalls. Port address translation in particular is a lot easier to set up on a router than it is on a lot easier to set up on a firewall than it is on a router. It's 2 statements, whereas in a router it can be 3, 4, 5 statements depending on how in depth you want to go. ACLs look exactly or very similar to iOS CLI. ACLs are written pretty much in the same and applied similarly. You have to have an access group. The thing with that is a difference in the ASA is that you don't have to go into an interface to apply your ACL. It's done in the global configuration mode, not in interface configuration. And finally, modular policy framework. This is similar to the iOS feature set that we talked about in the last class. It gives you the capability of intrusion prevention systems, deep protocol inspection, deep packet inspection, quality of service, rate limiting or policing, and TCP connection settings and timeouts. It goes over those configuration steps in page 190 through 192. You may have one question like this on your final. We'll get to it later into Lab 3. Questions? If there are no questions, we're going to dive into Lab 2. And in Lab 2, you have to have, we're going to spend probably 50% of our time on question number 1 and number 2. It's a routing refresher. Who had me for 347? 347. So we went over OSPF, a little bit of redistribution maybe, talked about that some. We're taking that to the next level tonight. Alright, so first off, what you need to do is get a VM. Okay? And your VM, I don't care if it's 2003 or 2008, this is what you're going to create your ACS server on. Under virtual machine and your virtual machine settings, you want to make sure that the network adapter is set to host only. Host only. Okay? And in your virtual machine, you want to make sure that the virtual net that it uses is configured to the inside of R2 or the 192.168.50 network. Otherwise, this is not going to work. I hope I got this set up. I did this with VM Workstation last class. I'm going to try it with server this class. Ugh. So there's a couple of checks we're going to do. Anyway, open up GNS3 and start a new project. Let's just call this CIS 467 LAB2. Save in VRAMs and virtual hard drives. Okay. Real quick, 3 routers, a switch. This down here is actually not going to be a switch. It's going to be a cloud that we're going to turn into a server, and this is going to be a virtual switch. We're not going to connect anything up here. So, router 1, router 2, router 3, switch 1, switch 2 that we're going to delete, switch 3, and a cloud. Now, configure the cloud real quick. This is going to be our connection to our VM. So, what I want to do here is I want to search for that VM that is going to be mapped to the same network as 192.168.50. Right, in this case, I've already pre-done that in the VM network utility, so I'm going to attach it to that. Click Add, click Apply. Okay. Now I'm just going to, for posterity, change the symbol, make it look like a server. Now I'm going to connect everything. I'm going to put all the F01 interfaces to the central switch. And all the outside interfaces to the local area networks, or the 00s to the local area networks. Okay. For giggles, I'm now going to read through the entire lab. This is really good practice to see if you have any gotchas. Alright? For those of you who are going to go for your CCNA or CCNP one of these days and you come across a lab question, don't just jump into the lab question and start configuring. Read the entire question. Because they may say something at the beginning and then change their mind and tell you to do something different towards the end. You have to read the entire question. I do that in here on purpose. IP the routers according to the diagram. Ensure that you give them the proper host name. Create the routing protocol domains according to the topology. Ensure that you have full 100% connectivity between all routed networks. Consider all networks to be routable from R1's Ethernet interface. That includes this network here called the Internet. Get into that later. I'm sitting here waiting. I'm going to turn all my routers on. Get them warmed up. Question 2. Create the routing protocol domains according to the topology. And I'm sorry, we already went over that one. 3. Block any routing of RFC 1918 networks to the Internet. We're going to do that on R1. That's the same exact access list that you had in Lab 1. But you have to apply it to the right interface this time. Create those NAT statements, they're static NAT statements. Create a PAT, or port address translations, tied to R1 serial interface. Okay? Have R3 set up a DHCP pool. 192.168.50.4 is your Active Directory / ACS server with the following credentials. Make sure you have username and password on there, and have R1, R2, and R3 authenticate to the AD server via ACS. You can use AD or local authentication, local database authentication within ACS. Either one's fine. Create an access list on R1 as follows. Remember that you used NAT previously. Allow okay, use all these different policies that you're going to create in your access list. Apply to the proper interface. And finally, an OSPF Area 0, incorporate area authentication with an MD5 key password of Cisco. Okay. So, there's one gotcha here. Re-IP your 201.68.109.128/25 to 201.68.109.128/29. So, that's why we're going to read it first. Before we address everything, we're going to have to make this change. It'd be wise to make this change. So, console to all these. I'm going to start on R1 with my outside interface, and I'm going to IP it. My outside interface is 201.68.109.98. Oh, I'm sorry. Thank you. Not a problem. I get carried away sometimes. So my interface is going to be addressed IP add 201.68.109.98 30-bit subnet mask. Turn the interface on. My inside interface is .129. That's F01. Add 201.68.109.129. /29 subnet mask. Let's turn that one on. Okay. Now, from here, I need to start working on my OSPF routing domain, area 0. So I'm going to exit out of there and go and do the router OSPF 100, which is my autonomous system or my process ID. That's going to initiate the OSPF routing protocol. I now have to tell it what networks to participate in. I only have one network in R1 that's tied to OSPF. And that's 201.68.109.129, or 201.68.109.128/29. So, I'm going to type in the network command, 201.68.109.128, and I have to give it the wildcard bits. So a /29 inverted is what? Well, it's not 255.255.255.248. If it were inverted, it would be what? 0.0.0.7. Good job. And then I have to tell it what area that this network is participating in. What area is that? Area 0. So we're going to leave that for now. We're going to go to, let's go to R2. Going to take T. Now, we've got to do the same thing. So in interface F00, it's participating